So the first unit that we're looking at is limits. And basically the idea of a limit is similar to, you've seen it before way back in grade 11 when you did infinite geometric sequences in series. So one of the examples that you might have done a long time ago is, say right now I am a certain number of tiles away from the wall. And if I were to walk half the distance to the wall and count the tiles that I walked, looks like I walked 8 tiles. And then if I were to do that again and walk half the distance, I'd walk 4 tiles. And I'm still 4 away. And if I walk half the distance, I do 2 tiles. If I walk half the distance, 1 tile. And then a half, and then a quarter, and then an eighth, and a 16th, 32nd, 64th, and so on, and so on, and so on. And if we would look at that sequence that we just talked about, I started walking 8, then 4, then 2, then 1, then a half, then a quarter. And the idea of this going on forever. Will I ever hit the wall? No. Because each time I get halfway closer to it, my new distance I cut in half again. Now, if I were to do this 1,000 times, I would get really, 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 really close to the wall, but I still wouldn't be there. But the idea of a limit says if you were to do it forever, I would eventually be so arbitrarily close to the wall that you'd basically say I was at the wall. And a reminder of this from your grade 11, you had a formula that said the sum of an infinite geometric sequence is the first term over 1 minus r. And if we use the formula, each time I was cutting it in half. And so I would have 8 divided by a half. Dividing by a fraction is the same as multiplying by the reciprocal. And we get 16. Now, we didn't need the formula to say 16 because if you imagine, if I walked half and I walked 8, how far away did I start off with? I started 16 away from the wall to start off with. And when I walked 8 halfway, and then halfway 4, and then halfway 2, and so on, you could see that eventually I'd get really, really close to the wall, and the wall was 16 away from where I started. The formula shows it as well, but that idea can be seen just by looking at it. So we would say that that is the limit. A limit is a value that you can get arbitrarily close to. This comes into math, and we're going to look at it because sometimes there's things in math that you're not allowed to do. What are some things in math you're not allowed to do? Divide by 0. Probably the most famous one. Got a picture up here on the wall of someone who did that. You can look at the disaster that happens when they did it here. Can't divide by 0. But sometimes interesting things happen when you get close to dividing by 0. So if I can't divide by 0, right, what would happen if I divided by 0.00001? If I got really close to it. And then seeing what happens when you do that. And that's another thing that we're going to be looking at when we look at this concept of limits. Now, there are 2 types of calculus. The first 2 units that or actually the first 3 units, look at differential calculus. And the second one looks at integral calculus. The main difference, they're connected. Differential calculus, what we're really looking at is tangent lines on curves. And it doesn't sound like that much, but it's amazing things that we can do with that. So what is a tangent line and what is a curve? Here is, let's say you have a sine curve. What would happen if you pick this point and drew a tangent line? And calculus is looking at what is the slope of that tangent curve at that point. Now that seems like, why would I want to know that? Like, this is interesting, an interesting thing to design a whole course around. But what it will look at is slope is a rate of change. how fast things are changing. So with this, we can figure out certain questions like if I'm draining, if I have some sort of cylinder that has water in it, and the water is draining out at 3 milliliters per second. That's a rate of change. Okay? Now, depending on the shape of the cylinder, maybe it's a cone, the height of the water will be coming down slowly at the beginning, but speeding up as you get further and further down because the cone is getting narrower. So we'll be able to figure out with calculus how fast the height is changing at any given time. And we'll be able to use these ideas to solve all sorts of real-life applications for things that would have been really difficult using the mathematics that we've developed up till now. That's differential calculus. Integral calculus is about finding areas. So for example, you know how to find the area of a rectangle. We have a formula for that. We have an area of a circle. But if I wanted to find this area under this sine curve, it gets a little bit difficult because it's bendy, right? Or you took parabolas in grade 11. Here's the parabola y equals x squared. If from 1 to 3 you drew this, what would that area be? How do I figure out that the area under this parabola is, well, it looks like 5. Might have to check the math. No, maybe it's 4. Yeah, it's probably 4. So those are the two branches of mathematics. So we've got the one that has areas of curves, and there's some history there. Archimedes, famous mathematician, developed it. He called it, another guy called it as well, a method of exhaustion. This idea of if you can't find the area because you don't have the formula for it because it's a curve, why don't we just make a bunch of tiny, tiny rectangles that's close to the shape that we're doing and add them all up? And if we keep making our rectangles tinier and tinier, so here's our parabola again, right? This is the curvy part, but if I just make a bunch of little rectangles like this, and I use my area formula for rectangles, I'll get pretty close to the right area. I'll just be off by a little bit of the error that happens with those rectangles up at the top. But if I made my rectangles smaller, then I would be even closer. And if I made them smaller and smaller and smaller and kept going forever, just like the limit, then I'll eventually get the perfect number for the area. And then I already said that differential calculus, which we'll be doing first, has to do with tangents. And it was simultaneously discovered by Newton and Leibniz. Now there's arguments over this for a long time. If you ever got a textbook that's origins were out of England, they would always say that Newton discovered calculus. If you had textbooks coming out of Germany, then they would always say that Leibniz discovered calculus. It is the current belief that they both discovered it on their own, albeit at different times. There wasn't like Twitter at that time that they could just like, got it, calculus, yeah, I was first. So there, I don't know how many years apart they were, but they both are credited with solving at the same time. Okay, so that's some intro stuff, but now let's actually do some review of math. Do you remember how to factor? And we get into some factoring that you might not remember how to do. So try this one. Most of the time, people will think of 6 and 4 first. It seems to be good because 6 times 4 is 24. And 6 plus 4 is 10. So you feel really good about putting x and 6 and 4 because it seems like everything is working. But then the negative sign causes a problem because you can't make them both negative because that would make the 24 positive. But if you make one of them negative and the other one positive, when you go to check it, this is equal to x squared plus 2x minus 24. So 4 and 6 causes a problem. And then if you switch the minus sign to the other way, you get a minus 2x. But if you thought of 2 and 12 first, how many people thought of 2 and 12 first? Lucky. Then here, the 12 would be positive, the 2 would be negative. And when you multiply that out, you do get the plus 10x. How many people are coming from French immersion? Okay. So coming from French immersion, one of the things that we use in English to help us remember how to multiply this out, because you remember multiplying like this and like this and like this and like this, and what do you use in French for that? What do you say? You just distribute it, or right? In English, we use a fancy word called FOIL. Have you heard of it? Okay. The fancy word called FOIL is because you multiply the first ones, the outside ones, oh man, the inside ones, wow, inside, and the last ones. So you might hear me say FOIL every once in a while. All right, have a good day.